So I'm just going to read a quick bio about Abe. So Abe is still a core contributor. He is a core contributor to the Great Expectations open source library and a founder and CEO of Superconductive, the company supporting the project. Prior to Superconductive, Abe was chief data scientist at Aspire Health, the founding member of Jawbone Data Science team, and lead data scientist at Massive Health. Abe has been leading teams using data and technology to solve problems in health tech and public policy for over a decade. Everyone, fighting pipeline debt with great expectations, Abe Gong.
Great. Thanks, Shervin. And thanks everybody for being here. I'm sure we've had lots of jokes about being here virtually. This is an interesting format. I know for me, it's going to be a little bit tricky giving the presentation without being able to see everyone. So if you just be vocal in chat, speak up. I don't know that I'll be able to hit everything as we're going through, but yeah, the more questions, more feedback you can give, the better. So I'm here to talk about fighting pipeline debt with great expectations and just making sure that you can see what I can see. Okay. So we've done an intro. We don't need to do that again. The one thing that I'll add is just that I care a lot about not just data, but data as it affects humans and data as it kind of touches human systems. And so kind of human scale ethical data is a real passion for me. And a lot of the kind of thinking that goes into great expectations actually reflects this balance, tension. I don't know if it even is a tension, but the idea that if we really can do excellent technical work, hopefully we can also use that to do great human work and use it for good causes. I know that's not always how things play out with technology, but as much as possible, I really like the idea of empowering people to embody good values in technology. For today's talk, we're going to touch on three things. One, what is pipeline debt? So frame the problem. The second, how does pipeline debt play out in practice? And I'm just going to talk through, partly from a machine learning perspective, but also just data engineering in general, what technical debt looks like in data pipelines. And then last, I'm going to talk about Great Expectations, this open source project, and how it helps beat pipeline debt. So what is pipeline debt? I like to put it this way. If you were a software engineer and you were developing an API, and you come up with an API and you want people to use it, and you went to a bunch of potential users and said, hey, I've got this awesome API. I would love for you to use it. But there are a few things you should know before you start. The first is it's not documented. So, you get the API, it's there, it'll return stuff when you ping it, but I don't have any good documentation for that. And then second, oh, by the way, it's not under test. Sorry, we just, for reasons outside our control, we couldn't test the thing. And then last, it's also not stable. Like this API is going to change at some point in the future. I actually might not know when that happens. So, just be ready for that. Yeah, it's not documented, not tested, not stable. If you pitch that as a software engineer, you'd probably be laughed out of the room, right? Your constituents would say, you are absolutely crazy, right? Like you have a prototype at best here. Don't ask me to rely on a thing that just hasn't had this core engineering work go into it yet. So I'll put it out there. That's kind of the state of software engineering today. On the flip side, if you make one little change, if you say, hey, I've got this great table in my data warehouse, or I've got this great machine learning model, and I would love for you to trust the results to guide business decisions or inform the workings of a company. However, it's not documented, it's not tested, and it's not stable. Weirdly, we have somehow persuaded ourselves that that is a normal way to be, that it's okay for data products that are now core to all kinds of business decisions and all kinds of product delivery to not have documentation, testing, or even be stable. So I'll just throw it out. Like I think we've kind of frog boiling in water gotten to this world where we pack a lot of really important logic into data pipelines and into machine learning models, and yet most of them, and I say this kind of blaming myself as well. Most of them are not yet built to the standards that we consider normal in other parts of software engineering. And the consequences of that is that the systems are really hard to maintain. They break. If we were in person, I'd ask for a show of hands. but I kind of know what the answer would be. Like, I suspect that almost everybody in the room has had an experience with a broken dashboard, for example. So some key metric that was relying on a somewhat opaque data pipeline where something changed and it broke. I can't tell you the number of kind of scary data stories that I've run into around machine learning models. I've heard about machine learning models that were deployed upside down and backwards in production, or almost every team that has used machine learning based on logging, right, using data exhaust from logging, has had the time where the logging team changed their enums, and suddenly you couldn't trust the values coming out of the machine learning model anymore. So like there are a lot of reasons why these systems break, and most of them come down to this notion of pipeline debt. It's just we don't have the systems in place to be able to test and document and guarantee stability. And I put it to you that operating in that environment is pretty crazy. And I really want to get to a place where, 2 years, 5 years from now, we look back and we say, wow, so glad we're out of the dark ages of 2020. And now, our data systems actually work all the time the way we think they should work. So let me play this out in a little bit more detail. So how does pipeline debt actually play out in practice? And I want to do sort of a generalized worked example, so that I'm not just speaking in abstraction, so we can get a little bit closer to the kind of the core workflows that actually play out here. So imagine a DAG, and I'm assuming everybody in the room knows what a DAG is. Like a data pipeline flows top to bottom, directed acyclic graph. But the idea is its data flows. And so without kind of naming exactly what the pieces are here, imagine that this is some kind of ETL and normalization pipeline. So these blue nodes at the top, let's say those are 3 tables that are coming in as raw data from somewhere else outside your control. And then you're going to do a little bit of merging and joining to make them work together. You're going to do a little bit of cleanup, and you're going to pipe those into 2 tables in your data warehouse, say. So pretty small initial projects, depending on the scope. This might be a couple weeks of work to get it running. Depends on the tooling you're using, depends on how familiar you are with the data. But there's some work to build this first little part of a system. Okay, what happens after that? You can actually characterize it pretty crisply. What I've noticed is when data systems grow, or when data systems work, rather, they grow. And when they grow in 3 distinct interconnected ways. One way they grow is they get deeper. So as soon as we've got those tables in our data warehouse, somebody's going to say like, okay, it's great that we've got this raw data here, but I actually want to derive some insights from that. So can we do some aggregations? Can we do some grouping? And maybe let's generate a report that we can then share with somebody else in the company. So the system gets deeper. You add more layers down. Second way the data systems grow is they get wider. So somebody comes along and says, hey, it's great that we've got this data warehouse working now. In addition to those 3 raw tables we were bringing in before, I've got 2 others. And if we bring these in, we can actually start to build an alerting system for some of our products. So let's do that. Let's add an alerting system. So we've now got another chunk of data here. And let's keep going. I'll call out that there's a gap here between one team that's building out the alerting system and the other team that's building out the initial ETL and reporting. Okay, so deeper, wider. The last way that data systems grow is they grow thicker. So let's imagine that down here, bottom right, we're now building a machine learning model. And I think machine learning models they're not unique here, but they tend to be a little bit different in the sense that for machine learning models, you tend to want to bring in features that touch a lot of different aspects of the data. ML, like almost by definition, you're looking for signal in a lot of different places. And what that means is if you diagram out the upstream data sources, ML models have this special property of doing a lot of silo busting, a lot of complexifying, is that even a word? Like making your DAG more deeply interconnected. They make the connections thicker. And that's a good thing, right? Like, I mean, we've had generations of data scientists, BI folks, and data engineers all trying to bust silos and make it so information is shareable and kind of usable across organizations. However, you have to realize that when you do that, you are also, by definition, making your DAG complicated and interconnected. And I'd argue that's necessary complexity. It's good complexity, but it comes at a cost. It's hard to maintain. And here's how that tends to play out. Oh yeah, so your data wants to be a hairball. It's kind of a fun way to say that. And you should let that happen. You should just be ready to maintain it. Okay, so you've now built out this data system. This, depending on exactly what's gone into this could easily be a few months worth of work, maybe even more. And then one day, a dashboard breaks. One of those reports that you were building before, something goes wrong with it. And somebody comes shouting at you from another team and says, "Hey, my dashboard's broken. What's going on?" Maybe it's the director of sales, and she's saying, "Hey, last week we were all on track to meet our goals, and this week it says that we're all 30% short. Now I've got 30 salespeople asking me where their bonus is going to come from." Okay, so now you as an engineer have to dive in and say, "Okay, I don't believe that our business just tanked 30% overnight. So something else must be happening here. There must be some kind of glitch in the data system. Okay, where could that be coming from?" And when you look at it, that glitch could be coming from almost anywhere. And when I say almost anywhere, what I mean is you have to do this root cause analysis where you identify the problem, and then you trace backwards from there to figure out, okay, where in the system, like what in the system changed to cause that problem. And it's not uncommon when you dive in to discover that for a downstream data source or a downstream data report, something like that, often 20 or 30% of the full data system upstream of that could be potentially implicated in a kind of deep, wide, and interconnected data system. So root cause analysis suddenly could sprawl all over the place. Making it even worse, we talked before about this notion of a team divide. Imagine that your team is responsible for the stuff on the left-hand side. So, the 3 data sources that came in, flowing down to this report. And then that other team that's responsible for alerting is on the right. There's this, I think, correct but pernicious dynamic that often shows up where, as a good engineer, you don't want to go and blame the other team for wrecking your data system. You want to make sure that your house is in order first, which means that you're going to run down all the possible causes in your data system first. However, as a practical matter, it's actually more likely that the other team caused your data problem. And the reason for that is, if you had caused it, you probably would have known, right? You already have expertise in your systems. You know how they fit together. At least you're aware of most of the changes happening there. So it's actually more likely that the problem is data flowing in from another system, some change that was made in an upstream system or a sibling system. But as a matter of course, we're trained as engineers to not ask outside our groups until we've run down all the potential problems internally. And because of that, very likely you're going to spend, a day, 2 days running down potential issues internally, maybe longer, depending how complicated the system is. And then you go to the sister group and say, "Hey, did you change something in your alerting system? Because something in our system broke." When you add this up, what you come to is this picture of what I call creeping exponential maintenance burden. So there's the upfront cost, this kind of hill at the front to get your data system built. And then once it's built, it grows deeper, wider, thicker. And as it does that, the number of potential unintended consequences in the system grows. It grows slowly, but it grows exponentially. And over time, it's not uncommon to find that you're spending as much time chasing down data issues and trying to figure out root cause as you are actually building new systems and delivering new value. So thesis, how does pipeline debt play out in practice? As your DAG grows, unintended consequences proliferate, leading to creeping exponential maintenance burden. Okay, so what are we going to do about it? I'm here to share this tool called Great Expectations. I'll give you a little bit of history. This started as an open source tool 3 years ago. Still is open source, always will be open source. It was a collaboration between a friend and I. We both saw this same issue in very diverse, very different data systems and said, "Hey, we think we can beat this, and we think we can beat it the same way that we beat technical debt in other places, through testing." So let me walk you through the kind of core philosophy of Great Expectations, and then I want to save some time at the end to ask questions and just make sure that you have a chance to respond. So earlier, somebody asked in chat, why is it called Great Expectations? It's called Great Expectations partly because my wife is an English major and she's a Dickens fan, and Dickens was close to hand. But mainly because the core abstraction in Great Expectations is a thing called an expectation. So it's an assertion about data. To answer another question that was asked in chat before, no, this is an assertion about data. So it's not a unit test. It's not an integration test. Expectations can be used that way. But crucially, we're not testing the software here, we're testing the data. And the reason to focus on data in data systems is so much of the complexity lives there. One of the, I think, key kind of mental breakthroughs that we had to make for Great Expectations to become what it's become is to realize that in a data system, testing the data is at least as valuable as testing the code. And you do that like so. So some of our expectations are things like expect column to exist. Really, really simple. But I suspect that a lot of us have seen data systems break because somebody renamed a column in a CSV and suddenly you had to import it just a little bit differently. Expect table row count to be between. So if you want to guard yourself against bad joins and merges or weird deduplication logic or things like that, just verifying that your table row counts fall into an expected range can be super helpful. We do other things like expect column values to be unique, to not be null, to be between, to match regex, to match string time format. And I'm just giving you a flavor here. The open source project has almost 60 expectations now, and it's set up so that it's pretty easy to create your own. And over time, we expect to see quite a bit of growth in the types of expectations that can be built and shared. Column mean to be between, column KL divergence to be less than. These are both more statistical tests. They allow you to test batches or windows of data. KL divergence is really fun. It allows you to take a histogram and assert that future distribution of data will be close to that histogram according to a KL divergence test. And we have other tests depending on whether you're using categorical or continuous data. And so on and so forth. So the notion here is to be able to do a combination of everything from like basic schema checking to more testing the content and internal format of data to statistical properties and even more advanced things. So we have teams that are starting to play with correlations. We have a question. Could you please provide a link to the repo? In good time. We're like, I think only 3 or 4 slides away from that. I'll get there very shortly. So that's the notion of an expectation. This is not new to Great Expectations or to data pipeline testing specifically, but tests. Oh, thank you. Somebody's just added the link. I love it. Interactivity is so good. Tests bend the maintenance curve. So they change the total future cost of maintaining your system. And basically they make it so you can build things once. And it's not that they will always and forever work. It's just that if they break, you'll be able to track down the problems much faster and with much more confidence. Okay, so that's a core concept. Let me get into some of the bells and whistles, other specific decisions that we've made in Great Expectations. So your docs are your tests, and your tests are your docs. So on the left, we've got a Python expression of a specific expectation in Great Expectations. So expect column values to be between room temperature. So we're expecting that it's going to be between 60 and 75 degrees. So we're in the US here. We're not in the UK. And we're going to say mostly equals 0.95, meaning we want to assert that 95% of the values will fall into that range, but we will accept some outliers. One of the things that we've done in Great Expectations is we've insisted that all expectations be declarative. They're expressible this way. And one of the features that comes from that declarative language is you can translate back and forth between expectations, the machine readable expectations, machine executable expectations, and really nice, clean, human readable documentation. So for example, this expectation can be expressed as sort of an assertion. Values in this column should be between 60 and 75, at least 95% of the time. You can also say, hey, warning, more than 5% of values fell outside the specified range of 60 to 75. And what this does is it really opens up the scope for what you can do with this tool. because it's not now solely an engineering tool that allows engineers to test their system. It's also a documentation tool, right? It solves another problem that we've had. If we were in person, I'd ask how many teams here have seen a data wiki that was always out of date, that was just constantly trying to keep up with the current state of the data. In the Great Expectations ecosystem, we think we've got a pretty great solution to that problem, which is that your tests are your docs and your docs are your tests. And as long as you are running your tests, which, of course you are, your docs will always reflect the current state of the data. Okay, we've got a bunch of really good questions coming in. I'm going to hold these until the end. Keep asking them though, and I'll tee them up. All right, so docs are tests, tests are docs. That's one feature. Another feature is what we refer to as automated data profiling. And I actually want to back off of the language of automated a little bit, because we don't believe that you're ever going to be able to drop your data in a black box and magically get all of the right tests and documentation. There's always going to be thought there, right? If that weren't true, then data engineering would be a pretty rote job. And I think most of us actually think in our jobs. So think of it as semi-automated or kind of computer-assisted data profiling. And the notion here is that our expectations already embody a lot of the information that you would want to capture in really good kind of metadata-rich documentation. And since we've got the capability of translating to human-readable formats, which, by the way, includes graphs and HTML and more sophisticated stuff than just sentences, we can use automated profiling to extract a lot, not all, but a lot of really useful information from the data. And then from there, we can continue to push forward and build out our testing and our documentation. So I'll throw out data profiling is still very much in active development in Great Expectations. There's still a lot of work to do here, but there's enough here that you can unlock quite a bit of value very quickly. And we're really excited to keep pushing on it. Third thing, batteries included setup and configuration. So we've got this command, Great Expectations init, that will go through and walk you through the basics of setting up a data system, or a Great Expectations validation system. So it will do things like help you connect to data sources, help you set up Slack notifications, help you configure your data docs. So yeah, anyway, a year ago, we were in a place where Great Expectations, the expectations were in pretty good shape and they could do cool stuff. Now we're in a place where I won't say every system and I won't say totally without friction, but lots and lots of tools now are nicely integrated to Great Expectations. And again, we continue to push on that and take the friction out of it. So if you have been thinking about building your own data validation system, I would strongly suggest that you consider using our out-of-the-box one, not necessarily because it will be perfect for you instantly, but because there are a lot of other people collaborating on it. It's getting better rapidly, and I'm pretty sure that even if it's not perfect, it'll save you a lot of time. And for some people, it is pretty perfect, and we love it when that happens. Last point is Great Expectations is open source. There was a question about this before. My team, Superconductive, we're the company behind Great Expectations. We also do some consulting work. We do data engineering ourselves. But Great Expectations as an open source product is always open source and will remain open source. And it's growing fast, and we're really, really excited to see that growth. All right, how do I get started with Great Expectations? Easiest way is to go to greatexpectations.io. Underneath that, you'll see links for getting to the Slack channel. We got last week, we crossed 1,000 people in our Slack channel. It's super active, really fun community. We've already got the link to GitHub shared in the chat here. If you have specific questions, we're starting to encourage people to ask those questions, not in Slack, but in discourse, because that will leave a paper trail and turn your temporary confusion into permanent learning for everybody else. And then read the docs for documentation. Let me throw in the documentation right now. We're doing a big push right now to bring it up to speed. Bring it up to speed meaning specifically, we're adding a whole lot of how-to guides because one of the pieces of feedback we got was that in the Great Expectations system, people want to be able to customize it and build it to fit their specific use cases. And so If you go in and you look and there's a how-to guide that isn't populated or isn't done, or anything else in the docs, please speak up about that. We're very actively looking to the community to help guide us in our prioritization of how we build that out. And it will all get filled in, but these things do take time. So under construction, and what my ask for you is just give a quick +1 or a quick like, hey, yeah, this would be helpful to me anywhere you see an article that's not done yet. So how does Great Expectations be pipelined at? Assertions about data, compiling to documentation, automated profiling, batteries included config and setup, and then a rapidly growing open community. Let me do a quick recap and I'll answer questions. So what is pipeline debt? Technical debt and data pipelines, mainly as a result of missing tests and documentation. Just throw this out, tell your friends, tell your colleagues if they haven't heard this message yet. We're gonna leave the dark ages pretty soon in the data engineering world. We're gonna get to a place where we are using testing and documentation, in large part because tools like Great Expectations are making it much easier to do that than it was in the past. In practice, pipeline debt plays out as DAGs grow deeper, wider, and thicker, which causes unintended consequences to proliferate, which leads to this creeping exponential maintenance burden. And the way to get ahead of that maintenance burden is through testing and documentation. And then again, I'd argue these are the kind of 5 big things that we're doing right now, with more planned in the future, for Great Expectations to help beat pipeline debt. So thank you. I wish I could see everybody, but I can tell from the questions coming in that you get it. And yeah, I'm really happy to answer on this. Let me go back through and start answering questions. Please feel free to jump in with others. And if I miss you somehow here, you can get in touch with us on Twitter through Expect Great Data. You can also get in touch with us on our Slack channel. Sorry, was that Shervin, was that you jumping in?
Yes, I joined to read the questions for you.
Oh, got it. Okay, would you? That's a great way to go.
So we got a ton of questions. I don't know how much time you have, Abe. We can continue the session over 10:30 if everybody's up for it and you're available, Abe. So
I am available.
Okay, awesome. So starting with Lynn's question, would it be reasonable to use Great Expectations to detect ML model drift?
Yes, and in fact, if you want to get a hold of me through Twitter or some other way, I can actually put you in touch with some articles that other people have written. There have been some great community examples of how to do that. Just to tee up the idea, the distributional expectations that I mentioned before are often a really good tool for that, because they're a like simple, direct way to be able to test your features and assert that the features are not changing too much. You can also, I'll throw in, test the output of machine learning models. And what we often see is this combination of test the upstream, test the downstream, to make sure that you have sanity checks on both sides.
Okay, thank you. So the next question from Antoine is, should you run Great Expectations on test data or on the real pipeline with real data, or both?
Really good question. What we're seeing from most people in the community is that most people test, they use it more like a monitoring tool first. So they'll test in production and verify that as data comes through, it still meets expectations. The reason for doing that, and I'll kind of give a framework for thinking about it. In traditional CI, what you're trying to do is you're trying to guard yourself against unintended consequences of change. And in traditional CI, the thing that's changing most often is your code. That's where most of the complexity lives. That's where most of the activity is. In the data world, the thing that changes most often and the thing where most of the complexity is actually the data. So on data engineering teams, yes, you will cause some unexpected breakages by changing your own internal pipelines, your own internal code, but it's much more likely that breakages are caused by a change to upstream data or format, content, whatever. And so most teams that we see using Great Expectations start by testing the data flow to make sure that when it changes, it's correct. Now, that said, as the internal logic for data systems grows, it also becomes useful to do integration and essentially unit testing of your own data pipelines. And so we also see teams doing that with Great Expectations. Neither one is necessarily better or worse, but the sense that I get from the community is that most of the value, or most of the initial value, comes from testing to make sure that testing in a monitoring sense more than a CI sense.
Thank you, Abe. So there are two questions about overhead and the size of the data that Great Expectations can support.
So we've seen teams running this on terabyte scale data. So big, and when I say terabyte scale, I'm thinking of batches. So if you have a terabyte of data arriving every night, you test it every night, then you're probably accumulating a lot more than terabytes over time. I would not claim that Great Expectations is like fully compute optimized. There are some things that we want to do in the future to make it even more efficient, but it runs quite, like, unless you have truly massive data, it runs pretty well. One thing to note is that I'll throw this. I don't think I mentioned this before, actually. We've built Great Expectations to be as agnostic to compute as we can. And what I mean by that is you can run Great Expectations on a Pandas data frame in memory. You can also run Great Expectations using SQL Alchemy. And if you use SQL Alchemy, then it actually compiles in a Python sense, but it converts your expectation DSL into SQL syntax and runs that in your Snowflake cluster, or against Presto or Hive, or wherever it is, MySQL, wherever it is that your data lives. So it's you don't have to push and pull the data and have a large I/O cost. You can just run it wherever the data exists. And then the third compute platform that we support today is, sorry, I'm blanking, it's Spark, so PySpark data frames. So again, however big your Spark cluster is, we can grow with you and support that.
Thank you. So there are two other questions regarding the operation of these assertions. So if I want to aggregate them, what happens when the assertion triggers, and can you dynamically change the sensitivity? Does it stop the execution or warrant, or is it in your hands?
So that's one where we want to just leave it open to do whatever you're going to do. The patterns that we see most teams using, some teams trigger expectations as warnings. So you run it after the pipeline has run. It doesn't interfere with the processing, but you get a report out that says, hey, check out these potential issues for data quality. That tends to be lighter weight to get started, and there is, of course, additional compute cost to calculate expectations, but it doesn't slow down the pipeline because you can run it after the fact. In addition, we also see teams doing things like plugging in expectations as airflow operators, or within the pipeline orchestration logic itself. And in that case, you can actually halt the pipeline if you want to. We're not opinionated, like we support both models because we think that both of those are very real, very useful use cases. And then we're also starting to see teams do things that I actually want to bring into the core project and have more first-class support for, running expectations on a row-by-row basis, and then kicking out rows that didn't match expectations into a triage queue. So if you have 95% of your data is clean, you flow that through. The 5% that was exceptional somehow, you can manually review that, or put it through some other process and then flow it back in.
That's very interesting. There's a follow-up question on that, and that is, does it integrate with any alerting and monitoring tools?
So we've set it up so that it's easy to trigger webhooks. We've got teams that are using it with PagerDuty. We've got one of the first things that a lot of teams do is just set up a Slack channel so that you can kind of be aware of the flow of data through your system. If you have ideas for other integrations, we'd love to hear them. What we found is that, building another webhook tends not to be super hard. And so if there's something else to integrate with, yeah, let's get that built into the open source system.
Awesome. There are two other questions about how does Great Expectation compare to other data validation tools? Yeah.
And I think I'm seeing references to Amazon's DQ project. And,
so there is DQ and TF data validation.
Both of those are perfectly respectable tools. I think what you'll see with DQ is, let me express it this way. Our ambition for Great Expectations is to be a translation layer, not just a testing layer. So the ability to do good profiling and then compile the documentation and multiple formats of documentation. That's a thing that I think is unique to us. The other thing that I think is unique is the ability to apply in this really broadly cross-platform manner. So lots of different SQL dialects, Pandas notebooks, also Spark, and just to be able to take the same language to all of those places and be confident that will work in the same way. That's, I think, a place where Great Expectations is really going to shine. Now, so I'm thinking about TensorFlow data validation. If you're doing all of your work in TensorFlow, if you're like purely in that ecosystem, TensorFlow data validation, like it's built for that world, and so maybe that'll work for you. But if you want this notion of an expectation and a test to be able to travel and span lots of different systems, I think that's the thing that we're really the only project doing right now.
Okay, awesome. I think we pretty much covered all the questions. If there are no other, oh, we just got one more. How Great Expectation manage cost control? Some of our Airflow tasks leveraging BigQuery SQL, which can be expensive for each run. Is there a cost-effective way to run it?
That's a really good question. To my mind, this ties in really tightly with the question about scalability and performance from before. Just to give a little bit more of a detailed answer there, there are basically two types of tests that you would think about. One is going to run on a row-by-row basis, and you need to assert that every single row matches that expectation. And for that, the best you can do is you can bundle your expectations together, save queries, and then just accept that the cost of computation and the cost of confidence in testing is going to scale linearly with your data. The other category of expectation is things that can be windowed or things that can be asserted about groups of data. And that's a really interesting world because suddenly you can apply sampling. So for example, if you want to assert that the distribution of data matches some distribution, you don't necessarily need to touch every single row. As long as you've got a good way to limit or downsample, then you can control your cost really aggressively there, right? Like if you have 1 billion rows, you might be able to learn what you need out of 10,000. One of the things that we made a decision early on in Great Expectations is that kind of blurs the line between those things is almost every single row by row expectation has this parameter called mostly that lets you assert that it will be true X% of the time. And as long as you're willing to tolerate a little bit of error, a little bit of wiggle room, what it does is, well, among other things, it translates that row by row expectation into a windowed expectation, which means that you can get the benefits of downsampling. So I'd say right now, really controlling performance and really controlling compute, it's a little bit of an advanced topic. It's a thing that I don't think we have great guides for, but we're definitely building the hooks into the core system so that you will be able to do that. And it's a thing we want to push on more. So again, I'd guide you to Slack on this. If you have specific questions, if this thing you're interested in engaging on, please get in there and start a conversation.
Excellent. Thank you very much, Abe. I think that would be it for the questions. And yeah, I guess we can leave the session open. If you like to stay, feel free to stay. There might be some events going on or chat going on. So, but I guess I'm just going to drop out at this point and feel free to, continue the chat.
Yep,
Thanks
I'll
again.
stick around for a few more minutes, and thank you for everybody for joining. Looking forward to seeing you on Slack.
Excellent talk. Thank you. Bye.